Good morning, everybody. Today is Wednesday, March the 10th, and this is the asynchronous portion for the students at North Toronto. I am, of course, Mr. Chen, and this lesson is on the inverse function and its properties. It's from section 1.5, found on page 41 of your textbook. Hopefully, you'll use your textbook as a reference, and let me just show you what we're going to be looking at. I'm not going to do the exact examples here, but they're pretty good. I do recommend you try the reflecting example 1 and example 2 at your own leisure. And we're going to see another aspect about why we're doing it, the inverse function. So I decided to switch to a Word document, and hopefully this is popping up this time. And let's first of all talk about some definitions of what functions are. As you've already learned, that function notation, come on, why isn't it writing? It's not writing. Function notation is f of x, right? So first of all, let's talk about the notation for inverse. This looks like f to the negative 1. So this is f at x, which a lot of you already know. And this f to the negative 1, you simply pronounce this as inverse. So some of you have seen this before on your calculators, perhaps, even as written as maybe as INV on older calculators. And you'll hopefully understand what we're going to be looking at. Let's go with a specific definition. If we have an ordered pair, x comma y, and if we want to perform an inverse transformation, and technically I should write f to the negative 1, so the inverse, what you're going to see is the swapping of the x and y coordinates. Notice what's written, y comma x. Let me give you a specific example. Let's just say we have this critical point, 2 comma negative 3, and let's just say we want to find its inverse. It's really easy, but if you want to pause the video to try to answer it yourself, go right ahead. And I think a lot of you understand the answer is negative 3 comma 2. It's that easy. So for our second example, let's just take a look at these 4 critical points of a function that we're going to do. Now, I just popped this up, and we're just going to connect the dots because we're going to make this a function. So this is our function. Again, hopefully you're going to do this with me. You're going to plot the points, and then, of course, on some graph paper, draw it out, and then record the critical points. Take your time if you have to. Again, pause the video. And I think a lot of you understand that the one critical point is negative 4, 0. The other one is negative 2 and 3. The other one is 1 and 3. And the last one is 3 and 1. And what I'm trying to show you for this one is actually the transformations for that inverse. So I want to actually get the inverse and talk about it. Now, the black function that you see, clearly it is a function because it satisfies the vertical line test. And what we're going to try to pay attention to is if you do this now for its inverse, and you see I'm writing in red, again, pause the video if you have to, but swap the x and y coordinates. So what do you see? Notice that negative 4, 0 becomes 0 and negative 4. And I'm just going to finish this off so everyone can see it. Now, what's the most important part of this is visually seeing that new inverse. And so let's plot them out. 0, negative 4 is here. 3 and negative 2 is down here. 3 and 1 happens to be right here. And 1, 3 happens to be like so. I didn't mean to do this. I just made this question up right now. And a lot of you can see that red function. But is it really a function? I think a lot of you agree that the inverse is not a function. Why? Because it fails the vertical line test. So one more time, not all inverses are going to be functions. If you really wanted to know a quick definition, if a function is a one-to-one, then its inverse will always be a function. So in this case, it's not. Now, the second property that you should be noticing from this is something kind of funny. And again, don't get me wrong, the points shouldn't overlap. It just so happened I've chose this points like so. And what I'm going to draw is another line. And some of you might see it. So hopefully I can do this. I might have to use the mouse. And let's just start over here. Like so. And let's just change the color so it stands out a little bit. This green line that I've drawn, I think a lot of you realize, it seems to be that the inverse is a reflection across the y equals x line. So inverses are reflections across the y equals x line. It's like that mirror image. And a lot of you might have to tilt your page. Finally, now that we've talked about how they look and how they swap from the fundamentals, xy maps to yx, let's talk about an equation. Let's say we give you this example, y equals 2x plus 4. This is clearly a straight line that you've learned already from grade 9. And just to visualize it, I'm going to sketch it really quickly over here. The y-intercept is up here, so it's 4. It's quite steep, not super steep, but that's our line, right? This is a function. It's a straight line. And let's just say we want to find the inverse equation. So what are we going to do? I think a lot of you understand what I'm going to show you. And if you want to pause the video, feel free to try to problem solve it. Some of you may want to do a table of values for that black function, the y equals 2x plus 4, and then swap them, and then graph it, and then find its equation. But there's a faster way. Watch what I'm going to do. Notice what I did? Just like, and I scroll back up, hopefully, a lot of you realize I just swapped the x's and y's in the equation. Now, some students say, is this the answer? Is this where we're just going to stop? I apologize for that thump. I fell a little bit. So this is technically correct, x equals 2y plus 4, but we tend not to express our equations in terms of its independent variable. We tend to solve for y, or express it as y equals. So we're going to have to do some algebra. I think a lot of you know what I'm going to do. Solving for y results in subtracting 4 to both sides. And then what are we going to do? Divide both sides by 2. And this is the inverse equation. Notice it's still a straight line. It should be a straight line. Now let me just show you what this looks like in terms of the graph. The slope of the line is 1 over 2, so it rises 1, runs 2, and it has a y-intercept of negative 2. Now where's negative 2? So maybe negative 2 is down here, and it looks something like this. And this is the inverse equation. And some of you are probably, where's that green line? And it's not the greatest, and I do apologize, but that's the reflection line. So I'm going to erase it right now just so that you can see it. And that's why if you tilt your head, the black line reflects across that green line, and that's why we get that blue line that I've just drawn. So to sum up this lesson, this mini lesson, one more time, inverse functions, hopefully you refer to section 1.5. Take a look at some of the practice questions and the 3 things that I'm trying to emphasize here. First of all, inverse really means swap y and x. Second thing, not all inverses are functions. And in fact, in this example here, we visualized and saw this. Third thing, we looked at actually, inverses actually reflect across the y equals x line. And the last one is understanding how to swap and write an equation of the inverse function. Have a nice day. Hope this helped, and refer to your textbook.